So I'm really pleased to be at this meeting. So yesterday, blown away by the images you all shared about the morphology and manifestations of cryovolcanism on various moons and icy bodies. And then today, hearing about lots of great models trying to describe the dynamics that create these kind of features is really inspiring. Because I come at this problem from a completely different place. I'm instead thinking about the stuff. So if you've got a little chunk of stuff, in this case ice, and it's loaded with all of its beautiful imperfections and impurities, perhaps melt phases, and at different temperatures, how it responds when exposed to some kind of stress. And that could be over various time scales, from your instantaneous elastic response to your, say, quasi-steady state long-term stress, like from, for instance, convection or tectonic loading, or in between those two, the kinds of stresses that Terry talked about, which is kind of the world I like to live in, that periodic tidal stress. And how does the system respond? And for the purposes of this week, I'm trying to think about sort of as a continuum in between this perfectly polycrystalline solid and a perfect liquid, this continuum in between. Like you might have, for instance, as temperature increases as for these icy bodies, like it would be with depth, or as composition it changes as you get more and more of some sort of an anti-freeze second phase. And to a lesser extent, maybe say time since eruption, because as I was talking to Jeff yesterday, he reminded me that when you're going in this direction, you could have in an ice-rich system, you can have dendrites and various faceted phases, and depending on your composition and your delta T, a lot more complicated stuff can go on. And with my own experience, I know that when you have a really big delta T and you freeze a liquid solution, you could sometimes get an amorphous solid. So maybe you've got this amorphous solid creating an insulating layer, and then you have increase in grain size as you go radially in. Anyway, this is all to say that in this direction, the situation is far more complicated than my little polka dots would suggest. So there are many mechanical properties that might be popping up inside your models. And I'm going to focus on a handful of the ones that I feel more comfortable talking about, and the ones that I've participated in measuring. And in particular, these mechanisms depend on a lot of microstructural effects, but for the purposes of this workshop, I'm focusing on temperature and melt fraction. So if you were over here living in this above solidus two-phase world, somewhere in the liquid plus ice field going up and down or side to side, and in particular, toward the end, I'm going to focus a little more heavily on friction and attenuation, in particular because those could be heat-generating mechanisms, and particularly I'll focus on if they are tidally forced mechanisms. And so hopefully by that way, I kind of create that segue to the rest of the session, which we'll be talking about once you've got the melt, what happens to it. So the first that I wanted to talk about, just very briefly, is about elastic properties, for instance, Young's modulus. You can measure a variety of ways. One of the common ways, though, is a non-destructive way in which you have a transducer and a receiver, and you send both P and S waves through the system, through the sample, measuring their velocities, and you can come up with this relationship for modulus. And this is just one representative two-phase system. This is ice plus small amounts of salt. And I just like this because I think it makes a nice clear example that temperature is increasing in that direction. And over here below the solidus, sorry, the eutectic melting for salts, of course, around -22. Below the solidus, the properties of both the V and the P and S waves are almost identical to pure ice. This is really a small amount of doping. But then you have this very precipitous drop right at the melting temperature, and then a more gradual decrease in the wave speed velocities with temperature, which would correspond to melt fraction as well. And there's a different path upon going which direction you were going in temperature. But, and then if you just look at, for instance, one constant temperature, but looking at various compositions, you probably have like a roughly linear drop with the amount of the melt present. And so I'm going to move on to viscosity, but just keeping this general shape where you've got this precipitous drop right at melting. So viscosity can be measured in a couple of different ways, depending on the amount of solid that you have. And this is the world that I feel comfortable with. These are the kinds of experiments that I've done in the past, where you basically take a mostly solid sample and you squeeze it between two plates very slowly at controlled stress, and you measure the strain rate over time. And this compares to another method when you've got more liquid than you have solid, and there are other people, Jeff, Carl, who are far more comfortable with this kind of process, but basically it's the resistance that the paddle feels as it's moving around in the slurry that provides the values. So thinking about far end member of pure polycrystalline ice, a lot is already known about ice. It continues to surprise us from time to time, but in general, we feel pretty comfortable that you can use a flow law that describes the stress and the grain size dependence of strain rate, as well as the temperature dependence using the activation energy, and that at least conditions that we can measure in the lab, that two general mechanisms dominate. At high stress, you'd have dislocation creep, that's just shearing of your individual grains, but at lower stresses, a form of grain boundary sliding, where the grains are kind of moving past one another. And at the low stresses and grain sizes assumed for planetary purposes, I believe that the idea is that the grain boundary sliding mechanism is probably dominating in a lot of situations. So that makes you wonder, so what happens for a mechanism that depends on traction on the grain boundaries? What happens when you've got some sort of an equilibrium melt phase at those grain boundaries? So what do I mean by equilibrium melt phase? The theory goes that for equilibrium, based on the relative interfacial energies for solid and liquid, you can come up with this dihedral angle that you can measure. That dictates the wetting angle of the system, but then you can measure that. And if it's less than 60 degrees, you would have what would be considered these interconnected pores in between various grains into these little tubes and channels. Whereas if that is an angle that is greater than 60 degrees, the melt kind of might get trapped depending on different compositions or melt fractions. And this is a nice work done by Jane Blackford, who took an SE image of ice plus saline system and then quenched it. So this is the melt got quenched in liquid nitrogen, and then the ice later sublimated away. And it just really nicely shows a real actual three-dimensional image of this theoretical configuration. And again, this is equilibrium, so the system had enough time to get to this happy place. You know, wouldn't hold true for really transient or immediate processes. So let's talk about some of how it affects viscosity. So again, with that ice plus saline system, this is an older study that looked at otherwise the same conditions, pure ice down here, and this was ice containing 7% melt, clearly at conditions above the solidus. And they show a distinct, over an order of magnitude, increase in strain rate, so that's a decrease in viscosity with this amount of melt. And there have been studies on our, this week, our favorite system, the ammonia plus ice system. And I just blatantly cherry-picked the data I wanted from these two papers on the airplane override over here. But I tried to get similar temperatures and similar strain rates so that they can be compared. And that would be a temperature just above the eutectic melting temperature. And you see a pretty, in this log linear space, a pretty downward shaping curve of decreasing viscosity with increasing melt fraction. And so why is that? There'll be a theory of contiguity that I'm going to tell you a little bit more about in a minute, but suggests that by having that melt phase that on the grain boundaries, that it creates kind of this superhighway. So if you have diffusion or things like that at the grain boundaries, it creates this fast path, so it speeds things up. And one thing we were also admonished yesterday was that although ammonia is prevalent, it might be in very small quantities, so we were cautioned. But I wanted to kind of point out that although composition is very important for things like fractionation and thermodynamics and reactions, for mechanical properties, the mechanical response is very much dependent on a melt being there, not necessarily a particular melt. And in particular, if it has like dihedral angles, in many cases, they will have like mechanical behaviors. So all of the ices that I'm familiar with, ice plus saline, ice plus sulfuric acid I measured, ice plus ammonia, a student of mine measured, all have this angle, ice plus plain water, all have an angle between 20 and say 45 or so, which coincidentally is very similar to the dihedral of olivine plus melt, as well as borneol plus melt that you're going to hear a lot about, because this is what I studied when I did my postdoc in Japan. And so in theory, even if we've got ice plus question mark unknown antifreeze, I think we can really learn a lot from any number of these analog systems, mechanically speaking. And so this is a general theory of just a two-phase solid built by Take and Holtzman. It's a three-part paper with math that I just totally goes over my head, but I take out the figures, and conceptually it's really beautiful, thinking about not necessarily the melt fraction, but the other end, so the contiguity, so the area of contact between ice and ice, or sorry, solid and solid grains. And as melt fraction increases, contiguity decreases, and how does that affect, for instance, the viscosity when it's applied, when some sort of stress is applied. And they come up with this prediction, which has sort of a precipitous drop and then a more gradual decrease with increasing melt fraction. And that depends on the dihedral angle of the system. And normalizing it the way they did, normalizing by the pure phase, I come up with, see, there goes the 10 to the minus 3 to 2. So that was there. Almost exactly the same magnitude of the response. The shape is quite different. And I don't know if that's because this one point that I cherry-picked, doesn't really capture something going on at the low melt fraction, or if this process, which is specifically designed for the math that they did specifically is for diffusion creep, and these are probably deforming and primarily in dislocation creep, if that affects the response. But at least for the magnitude of the viscosity drop, models like this can be really powerful. One question they had, though, was if there is a critical minimum of melt fraction that would give you this response. And I know this is working on the side that probably most of you don't care about, but I just think it's super exciting because a recent paper coming out of the Dartmouth group answers that for, at least for the ice system, it's an incredibly small amount. So they looked at just 1 to 15 parts per million doped ice with sulfuric acid. And although the kinds of results they saw, the softening they saw is not these orders of magnitude I was showing, in all of the results under all conditions, they saw a softening with the tiny bit of doped samples. And then they did some Raman spectroscopy and found that in all cases, or almost all cases, the acid was confined or found itself in these little tiny triple junctions. So now this sort of critical minimum is different than what you might have for instance, percolation theory. And I'm not going to talk about it this much, but I call your attention to work by Mark Hess, who's here. And, but they, using the same sort of dihedral interfacial energy calculation, can come up with this permeability. And of course, in this case, if you're going to be talking about fluid moving and transport mechanisms and things like that, then you definitely have to have this interconnectedness of the melt, versus the mechanical properties seem to just have little dots, and that seems to be enough. But let's go to the end you're probably more interested in, is when you've got mostly a slurry, mostly liquid. And this is just one. I mean, Jeff has done a lot of work on this. The group at JPL has done a lot of work, so I just picked one of the images, but showing here it's with temperature getting warmer, but that would also equate to melt fraction, a nice gradual decrease in the viscosity with increasing melt fraction. So that contiguity theory I was showing you before, that basically holds true to about 20% melt fraction, and then it kind of precipitously drops because that's when contiguity goes to 0. And so how that connects to this data, that one's kind of stalled at about 10 to the 9th Pascal. how it gets from 10 to the 9th to 10 to the 3rd, I'm not really sure whether that is gradually steep and gradual, or if there's some sort of, likely there's some sort of point by which maybe in this system the ice grains start to lock up and interact and kind of interfere with each other. But then that, of course, is going to depend on your thermal pathway, like what your chunks of ice that you're growing, what they look like. So I think there's still some exciting things to be learned. And I was happy to see the poster outside that Aaron and Carl are going to have a new project looking at a variety of these systems that are relevant to the icy satellites. So now moving on to a different mechanical property, moving on to friction. This is something I've been doing for the last 6 years at Lamont. We built this new apparatus to measure ice friction. And so it's a biax, 2 axes of deformation. And we're doing the classic double direct shear configuration, where we've got a central piece of ice that's going to slide between 2 stationary blocks. So we use this piston to apply a normal stress. And then we tend to work in position control, and we push it through with some known velocity. And what we're measuring is the resistance to sliding. So the shear stress, which is felt over these 2 interfaces with a load cell. And friction, the value I'm going to be showing you, is the shear stress divided by the normal stress. And this is one type of an experiment we would do. One kind of a velocity program that we would use would be to get it up to a steady velocity, and then that would hopefully the friction kind of levels out to some steady state friction. And then we go through various velocity steps up and down. We would also then maybe at various increasing durations, we would stop the piston and hold it and see how the interfaces sort of heal, and this kind of stress you would need to overcome, kind of friction you would need to overcome to get it back to steady state. And we analyzed all of those curves carefully, but here are some of the results as a function of temperature. For our first study, we were looking at kind of temperatures not really relevant to this group, but we were looking at more terrestrial glacier temperatures and sliding ice on rock. And although there's some small velocity dependencies that you can see there, it's highly dependent, we found, on temperature. And when it gets close to or at melting temperature, it drops precipitously to like 0 friction, as you can imagine, because you would have this entire melt film over your sliding interface. And so my recent work has been to focus, to get a different cryostat that we can get a lot colder, and to focus on the kind of cryogenic temperatures that you all care about. So we've been getting to lower temperatures, and these are consistent. The values that we're attaining, the blue squares, are consistent with previous work done by Erland Schulson at Dartmouth. And, but our new spin on it is, among other things, we are also adding other stuff to it. So there's a lot going on here. For this talk, I'm not going to be even talking about the amplitudes of forcing and all that kind of fun stuff that I did, but just looking at the average friction. This is what we drove, this is the velocity, but just the average friction of the response of pure ice versus ice plus ammonia, we see some differences. One thing is that at all 3 temperatures that we looked at, we saw about a 0.2 drop in friction for ice having this small amount of melt at its corners and triple junctions. So we looked at 3 different temperatures, all with just the 3 weight percent. And so one thing that was kind of surprising to me is that having that melt there didn't make it respond like this. It didn't just drop drastically. It had a very controlled. So there's still a lot of ice contact probably during the sliding, but yet some weak at spots with the melt that caused this reduced friction. So ultimately what I wanted to do, at our current state, our cryostat was able to do these temperatures. We're now doing some minor tweaks so we can get even colder. Ultimately, I want to get down to a couple of temperatures below the solidus, maybe up above and below the paratectic, and then see at what conditions I can get melting at the interface of what will be a purely solid material. Because frictional heating basically depends on the friction, but also on the normal stress and the velocity. So we'll try to look at what conditions would be necessary to create melt at subsolidus conditions. And ultimately, we'd like to work with someone and try to using these kinds of stress fields due to tidal stressing on pre-existing cracks, try to revisit the frictional heating model with this new experimental data and see if we can come up with sources of melting at depth. So switching gears a little bit, talking about attenuation. So in the kinds of models that Terry was talking about, when you've got tidal forcing, to try to calculate the tidal heating, you need that Q value. And so to try to give good values for that, we do experiments to try to come up with that attenuation. So I'm not going to get into the stresses that we're trying to mimic, but for our experiment, we basically apply a nice sinusoid in stress, and then the sample responds with a sinusoid in strain. And if it was a perfectly elastic material, which does not exist, it would be perfectly in phase, but all real materials have some sort of lag. And the greater the phase lag is the greater the dissipation, and that's what we're trying to measure. And so we do this at a variety of frequencies, and we get a spectra like this, which is this sort of low frequency dependent, not exactly power law relationship. And this is the study I did in Japan, where we were looking at a lot of different materials, just sort of thinking about polycrystalline materials and what is the response. And if you looked in just regular frequency space, how all of these were measured, they'd be all over the place. But we found that if we normalize them by the Maxwell frequency, which is for each one of these materials, normalized by the Young's modulus and the viscosity, that they all collapse onto a single master curve, which indicates that the same mechanism is happening. What is that mechanism? It has been agreed upon mostly that it is this form of grain boundary sliding, and in response to that that deformation, the grains start to move past one another, but right away they bump into each other and they get locked, creating stress concentrations. And then the system wants to relieve those, and so it gradually, with diffusion, diffuses away from that, relieving those stress concentrations. So the question, of course, is what happens to a grain boundary process like this when you've got melt? And here are some experimental results from that study. So just not in normalized, just in regular raw data. This was a pure system, and this was the attenuation with melt present. With just a small amount of melt, there was a huge jump in attenuation, and then increasing attenuation the more melt that you had. And so then when we take that data and we normalize it again by that Maxwell frequency, it all collapses. So it's the same kind of mechanism, but now that diffusion goes a lot faster because it's got melt. It's got a superhighway to travel through. And it's very similar to the viscosity results that we got. We got a precipitous drop and then a more gradual response. And so what I would like to say is that we've totally nailed all of the stuff about attenuation with melt. We were also, there's comparable results from this study with ice and brine. But other studies have located, at least at higher frequencies, a melt-specific, what they're calling a melt-specific peak, which might be due to squirt of melt going from side to side. Oh, goodness. Oh, that's good. But this kind of a melt-related peak is at much higher frequencies than you all care about. seismologists really care about a high frequency peak because that's right in their seismic range. But if we're thinking about tidal forcing that are at really low frequencies, these kind of master curve approximation can do a really good job, I think. And so this is now a cartoon of the data, but you get the general sense that this curve can shift this way and that way based on temperature. Higher temperature moves it this way, which if you're just looking at a specific frequency means it looks like it's moving up. Smaller grain size or melt also moves it this direction or up. So even though I don't do the kind of extrapolating up to like global models of heat production, I've heard Julie talk about it though, and I think the magnitude of it is actually quite small. But this sort of shifting suggests that you could have a kind of feedback system where if you've got some sort of localized high attenuation area, maybe that's higher stress or strain, then you can get higher temperature, and then you'd have higher attenuation still. Then if you got melt, it would. So that's just to say that there's a possible feedback that can create maybe localized heating and ultimately maybe localized melting. So that's actually all that I have. Just to say is that my goal in life is to, or as experimentalist, is to try to give you the values that can kind of fill out to give us ideas of what's going on in the crust, give you the mechanical strengths with depth in the brittle section and the ductile section, perhaps giving you sources of seismicity, and for the purposes of this group, thinking about, in these kinds of systems, heat generating mechanisms, whether that's in the brittle as friction or down in the ductile portion as attenuation. Yeah, so hopefully that was useful. Okay, thank you. Yes. Oh, Mike.
That was a really good presentation, and I think that your comfort zone of living, working down in the low melt fraction area is also of great relevance to this group because, as your results showed very well at a few tenths of a percent, or even you showed one literature paper where down to 15 parts per million impurities affects the effective viscosity. These trace impurities, whatever the impurity is, if it's a melt-forming impurity, could very well be one of the dominant factors in controlling the tectonics of relatively pure ice shell satellites. So I think this is really cool.
So I think also this is really cool. I'm trying to understand. So the presence of melt drops the viscosity.
Yes.
But it increases the attenuation.
Yes.
And the higher the attenuation, the more heat you produce from the same stress?
Yes.
Okay.
Right.
I would have just thought that a lower viscosity material would somehow, I guess produce less heat when you squeeze it. But I haven't really thought about this.
Yeah. I mean, so it's just about how it shifts, and yeah, because of the viscosity term and how that makes the curve shift with Maxwell frequency. Soft stuff over this way, and am I doing that the wrong way? Well, okay. Well, I mean, that's. The viscosity is significantly lower. You can just look at this, significantly lower for the melt phases, and they show much more attenuation. So, regardless of the shifting.
Have you thought about modeled or in some way calculated the rate at which small melt fractions of something, ammonia water or sodium chloride water, whatever it is, will drain from the crystal network?
No, I have not. I think that's more in the realm of maybe something that Mark might be thinking about, that sort of the drainage and the actual flow between. I haven't worked on that at all. I think maybe it's not as straightforward as we would think. Is that, I mean, maybe.
But it will depend on grains. Sorry. I'll add a slide on some of the permeabilities we've calculated for low porosity melt networks. But it will depend on the grain size critically. So, for example, the absolute values.
Yeah, I am wondering whether there's any chance that after, say, 1 million years, it's possible that an ice shell will retain traces of that liquid, even at the parts per million level, because those traces would be really extremely interesting if we could ever get our instruments on them, and they were able to study those melt traces down at, even if they're present at only, ppm levels.